Percent composition and molecular formula worksheet. What we're going to start doing here is coming up with empirical formulas for compounds. Now, an empirical formula is a formula that is in lowest terms. So for example, if we had a compound like C4H8, this is not in lowest terms. All right, if this were a molecular compound, this would be its molecular formula. All right, this is molecular formula. If I put this down into lowest terms, then we call it an empirical formula. So notice both of these are divisible by 4. They're also both divisible by 2, but to get it in lowest terms, the largest number that you can divide both of them by is 4. If I divide both these by 4, this becomes 1 and this becomes 2. So my empirical formula is CH2. This is my empirical formula. Okay? So what you're doing by using the percent compositions, just like you were just figuring out in the last worksheet, by using these percent compositions, you can figure out a compound's empirical formula. In other words, its formula in lowest terms. So let me scoot this up here, since we don't need that anymore. And we're going to do numbers 1 and 2 together. One has you finding the empirical formula, and the next one has you finding the molecular formula, which would be the actual formula of the compound. So for number 1, it says, what's the empirical formula of a molecule containing 65.5% carbon, 5.5% hydrogen, and 29% oxygen? So in your reading material, there is a sheet that looks like this, empirical formula, and it discusses what I just talked about with the empirical formula versus molecular formula. And then down at the bottom, it gives you a worked empirical formula example. So we're going to follow these instructions to do number 1 on the other page. It says, determine the empirical formula for a compound which is 54.09% calcium, 43.18% oxygen, and 2.73% hydrogen. So it says, first, divide each percent by that element's atomic mass. So we would take 54.09% and divide it by the mass of calcium, which they've done right here. So I take 54.09 divided by 40.08, which I get from my periodic table. Remember, the bottom number in the box tells me the mass, 40.08. And they get 1.35. They take oxygen's percent here, 43.18, divide it by 15.999, its atomic mass, and get 2.70. And then hydrogen's 2.73%, divided by the mass of hydrogen to get 2.71. It says then divide each of these answers by the smallest of the answers, and this gives you the subscripts. So if you look here, we've got our smallest answer was 1.35. So I'm going to divide all my answers by the smallest of the answers. So I take 1.35, 2.70, and 2.71 and divide them all by the smallest one, which was 1.35. Obviously 1.35 divided by itself will give us 1. 2.70 divided by 1.35 gives us 2, and 2.71 divided by 1.35 gives us 2.01. But because it's so close to the whole number that we need for a subscript, we're just going to round that to a whole number of 2. Now, had it been right in the middle, say this had been 2.5, we cannot have half of an atom. So we would have had to have multiplied all of our answers by 2 to get this to a whole number. But because it's so close to the whole number, we can just understand that there must have been a little bit of calculation error in these percents because they're rounded off to the hundredth that did not allow us to get exactly 2 when we did this math. So our answers here, 1, 2, and 2, become our subscripts for our compound. So there's 1 calcium, 2 oxygens, and 2 hydrogens, 1, 2, and 2. So we can write that as CaO2H2. Now if you happen to know that OH makes the polyatomic ion hydroxide, then you could go ahead and put O and H in parentheses and say, hey, there's two OHs here, and this would be calcium hydroxide. I don't expect you to know that at this point in your chemistry learning, so if you ended up with this as your answer, CaO2H2, that would be perfectly acceptable. Though if you do happen to see a polyatomic ion in there anywhere and you can do that, that'd be great. So let's do the same thing that we just did here on our problem number 1. So let me see if I can put this where we can see those steps from up above and see the problem that we're working on. It looks like we can. All right, so we're going to have our empirical formula, all right, for a compound which is this, but now we're doing it for 65.5% carbon, 5.5% hydrogen, and 29% oxygen. So it tells us, first we divide each percent by that element's atomic mass. So I'm going to write down carbon, hydrogen, and oxygen here. Carbon, hydrogen, and oxygen. And then I'm going to put those percents down. So 65.5, 5.5, and 29.0. And then I'm going to divide those by their atomic mass. Carbon has a mass of 12.011, so I write that down. Hydrogen is 1.008. And oxygen is 15.999. So all I have to do is plug these into my calculator to get my answers. So let me do that here. Clear this out. So I'm going to take my 65.5 divided by 12.011, and I get 5.45. I'm going to round it off to two numbers after the decimal. That's really sufficient. So 5.45. Then I take my 5.5 for hydrogen divided by its mass, and I get 5.45 again, really 5.46 if I round up. And then 29 divided by 15.999, and I get 1.81. So here's my smallest answer, so I'm going to divide all of these, 5.45, 5.46, and 1.81, all of them by 1.81 because it's the smallest. These will give me my subscripts for my compound of carbon, hydrogen, and oxygen. So 5.45 divided by 1.81 gives me 3.01. So I'm going to use 3 because it rounds off pretty much to 3. 5.46 divided by 1.81 is 3.02. Again, rounds off to 3. And 1.81 divided by itself will give me 1. So my subscripts will be 3, 3, and 1. So when I write out this empirical formula, I'm going to put them in order: carbon, hydrogen, oxygen, carbon, 3, hydrogen, 3, and oxygen, 1, which, remember, I don't write ones. Got into the habit of writing there. All right, so C3H3O, we don't write ones. So this is our empirical formula. We have answered number 1, we're done. Now when I come down to number 2 though, number 2 says if the molar mass of the compound in problem 1 is 110 grams per mole, what's the molecular formula? So I want you guys to remember, here's the molecular formula and empirical formula for the example that I showed you earlier. If I had an empirical formula of CH2 and I knew the mass of this, the molar mass of the compound was the mass of the empirical formula. In other words, remember when we did formula mass, we added up, like for this one it'd be carbon and 2 hydrogens. If I added that up and I got a number here, which in this case it would be 12.011 plus 1.008 times 2, and it gives me 14.027. Now if I were told that the molecular mass of the compound, right, the mass of the molecular formula was 14.027, then I would know that CH2 is not only the empirical formula but also the molecular formula, because this can happen. For example, H2O. Right? H2O is already in lowest terms. We know H2O is water. Since it's already in lowest terms, its molecular formula and empirical formula are the same, because I can't divide these any farther. So if I had this and I knew the molecular formula was 14.027, then this would also be the molecular formula. But in this case, it's not. The example that I told you guys about, this was divided by 4. So it means the molecular formula would be 4 times this mass, because the molecular formula for it, right, the molecular formula is 4 times bigger than the empirical formula, so the mass would also be 4 times bigger. So what we're going to do down here, we have figured out the empirical formula for a molecule, and we're going to figure out, is this also the molecular formula, or do I need to make these subscripts bigger to represent the molecular formula? So it says the molar mass is 110 grams per mole. Well, we need to figure out what the mass of the empirical formula is first. So I know that C is 12.011, so I can take my 3 carbons, would be 3 times 12.011, and that's going to be, I can put 3 carbons is 36.033 that I got right here, and I have 3 hydrogens right here, 3 hydrogens, so I'm going to do 1.008 times 3 and get 3.024, and then I have 1 oxygen, which is 15.999. When I add those all together, I get an answer of 55.056 grams per mole for the empirical formula. That's not the answer it tells us for the molecular formula. So I know that this is not both the empirical and molecular formula. It's only the empirical formula. My molecular formula should have a mass of 110, and this doesn't. So what I'm going to do, I'm going to figure out how many times I need to multiply this to get the correct mass by dividing them. So I take my molar mass, 110, and divide by my answer that I just got. So I'm going to take 110 divided by my answer, and I get 1.9979 blah blah blah. Alright, so when I divided 110 by my 55.056, I got 1.998, which, since I'm looking for a whole number to multiply these by, is going to round off to 2. So I know that my molecular formula is 2 times the empirical formula. So instead of C3, I need 2 times it to get that amount of mass. So I'm going to have C6. H3 becomes H6, and O becomes O2. So this would be a molecular formula that would have a mass of 110 grams per mole and an empirical formula of C3H3O. You guys are going to do that exact same process over again for numbers 3 and 4. Find the empirical formula first, then find the molecular formula. You'll practice more of this on other pages later. If you are still confused or have any questions, please feel free to ask.